Specifically, just derive it and then take a look at those types of problems that are related to them. So let's derive it together first. And it's up to you. You're welcome to watch or you're welcome to actually go through the process with me. But what I want you to think about is this. As we derive the formula, what steps do you normally apply in completing the square? And apply those here. All right, so does somebody want to open up the steps from completing the square that we had written last class in our notes? And maybe we can read through those as we do this and think about what we should be doing each time. What was the first step in those notes? What did we want to do before we could do anything else? The way to start this, when it was given with numbers, Morgan, what was it?
Move C over.
Yeah, we started by moving C over. And I told you that that was optional when you're applying this topic with numerical values. Well, with the derivation, you actually have to move C for this to work. So let's go ahead and move C over. So the second line becomes ax squared plus bx equals negative C. And look what I'm going to do. I'm going to leave a space. Okay, and I know it's not obvious to do that. You wouldn't think to do it, but we're going to add something there. Remember from earlier. We're going to tack on some value to make completing the square work. What was the second step of completing the square? What did we do after that? Numerically we did this, and we're going to do it variably now. What did we do numerically? We just took the quiz, right? So think about that. Yeah, we divided by a next. We divided by a. When dividing by a, this ax squared just becomes x squared. Well, if you divide this by a, those both have a's over them. So now I have plus bx over a equals negative c over a. So we divide by a everywhere. All right, first two steps done. Step 3. What was step 3 that we talked about? What do you do to complete the square after that?
You have the
And then
square.
you have whatever is here. Yeah, in this case, we're going to see that it's b over a in a sense. You have whatever this coefficient is in the front. Think of this again, if you want to. You don't have to write this. If you want to think of it this way as b over a times x, you can think of it that way to recognize that b over a itself is a number. b over a, if b were 10 and a were 5, b over a is just 2. So you have whatever this number is, this quantity b over a, have it, square it, and add it to both sides. What's half of b over a? How do you have a fraction? And we talked about this last class. Simplest way to have a fraction is to do what? Simplest way to have a fraction.
Multiply by half.
Yeah, multiply by half or double the denominator as a result. Good, we got an answer, and I like this. All right. So have the value and then square it. So we take b over 2a and we square it and add it to both sides. And to add it to the right side, I can just tack it right in front because I know this is a negative here. So this is like b over 2a quantity squared minus c over a. Alright, so remember that when you want to have something, don't actually worry about having the numerator, just double the denominator. It's the same effect. It makes more sense algebraically as well. I would not write 1/2 b, I would multiply b over a by 1/2, and as a result get b over 2a. And I'm going to square that and add it to both sides. Now, on the left-hand side, it looks like this is going to be annoying and really complicated. But if you recall, this can always be factored into x plus whatever this value was, but half of it. Remember we talked about last class. If this had been a 10, right? Imagine, if you will, this is a 10. You would have that to make it a 5, square the 5 to make this a 25. And then this would become x squared plus 10x plus 25. This would make this x plus 5, x plus 5. So really just half of this always goes here. And half of this is b over 2a. Not squared, just the b over 2a is going to go right here. That will always factor that way. If you don't believe me, FOIL it out. FOIL this quantity out, you will get back to this line right here. And that always works. On the right-hand side, right, if I'm going to square things out, I'm going to write this as b squared over 4a squared minus c over a. How come I can do that? Because I'm squaring everything inside of this parentheses. squaring everything inside of this parentheses. On the right-hand side, what do I probably want to have? What do I always seek when I'm doing an operation with fractions? I seek a common denominator. Multiplied by a over a and a 4 as well. So let's put a 4a here and a 4a right here. Make that a common denominator now. On the left-hand side, I still have this. On the right-hand side, I now have b squared minus. Now, I can put it all over the same denominator because it's a common denominator. The common denominator is 4a squared. This numerator becomes 4ac. For those that know the quadratic formula, you should start seeing similarities or familiarities with this now. If you know what the quadratic formula is, you should recognize something already. Now, it's not in the correct form yet, but the idea is, almost 3/4 of the way there. Now, if I'm solving for x, and we've done this in the last section, when I'm solving for x, what do I have to do next? To eventually isolate x or get x by itself, what do I have to do?
Unsquare the left-hand side and square root the right-hand side.
Yeah, so square root both sides. Remember that when we square root something in an equation for a solution, it's plus or minus. X is our solution part, so that we don't have to worry about because we're square rooting a square, which just makes the right-hand side this. The left-hand side this. Okay, that's the left-hand side right there. Now, the right-hand side is exactly what it looks like, but remember, when you square root something, you could square the top and the bottom separately. Yeah, so what's the bottom going to become? What is the denominator when you square root it become?
2a.
Simply 2a. And the numerator, I'm going to leave it under the square root. Okay, the square root of b squared minus 4ac, plus or minus. And again, recognize all over 2a. Quadratic formula, there it is. The last step is to take this and do what with it? Move it on over. Not multiply, be careful. Subtract. Because it's currently being added, not multiplied or divided, we have to subtract it from both sides. Now, to subtract it though, remember how that's going to look. I'm going to move this over right in front, right there. Always going to move it right in front. We talked about this earlier. And I'm going to say, okay, negative b over 2a. I'm going to write it like that. Plus or minus b squared minus 4ac. Well, it turns out that we have a common denominator without even having to worry about it. The denominator is indeed common, so we'll write it as one single fraction. And this is our quadratic formula. Okay, so it's pretty cool, I think, that when you show where something comes from and understand where it comes from, you understand its significance. The idea of completing the square is extremely useful because of what it just led us to right here. This generic solution for any quadratic. It's a very powerful answer to think about it. You could plug in any value for a, b, and c and come up with the solution from this one algorithm right here. Okay, this generic solution. Now, this is a quadratic. You can get a cubic equation solution. And there is a cubic formula. It is really long. And then once you get to quartic, you become solutions that are pages long, the solution itself. So obviously, we don't really go beyond the quadratic formula. We don't look at a cubic formula, really. Now, realistically, you could, but you would probably just solve it on a calculator. You would find the x-intercepts by graphing it, look for the zeros of the function, and those would be your roots. Now, obviously, if those roots are imaginary, we spoke about last class how imaginary solutions don't show up on a graph. We don't see the x-intercepts, unless for imaginary solutions. So we'll see in this year, in chapter 8, actually, how to figure out those problems, or how to deal with those problems. But again, this is the quadratic formula. If you didn't have it memorized or you don't know it from your previous class, you could sing, I think, Pop Goes the Weasel to it. And I know a lot of teachers do that. It's really lame, but it actually does work really well. When I was in, I think it was 8th grade, I had this? Yeah. In 7th or 8th grade, my teacher had us, like, as a quiz, we had to have this memorized. I mean, I can quiz you on it, but you need to have it memorized. I'm telling you that. You know, for this year, for next year, for the year after, for math, you have to. I don't have to really give you a quiz on it, but she would think of it as x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And it's really corny, but it actually does work if you have trouble with memorization in general. Or just please make some flashcards, okay? But memorize this formula. You have to have it memorized. Again, a, b, and c, what are they? What are a, b, and c? I know we had them in the original problem or the original setup, but what do they represent? A, b, and c. What do they represent? They are the what? Coefficients. Be careful. Because you want to say variables, because a, b, c, x, y, z, they're all letters. So you say variables, but they are the coefficients actually. Now, they can be variable coefficients in a sense, meaning they can vary, but they are the coefficients of the equation. Okay, they are the coefficients of the equation when set equal to 0. This is a simple one just to practice, then we'll get to an application of it. Okay, a very simple one. So we see we have 5x squared plus 4x minus 2. I could use AC method and try to factor this. AC would be negative 10. Are there any numbers that multiply to negative 10 and add up to 4? There are none. So factoring is not going to work, I know already. Okay, so automatically I go to my quadratic formula. Now, obviously, from section 7.1, you could solve this with completing the square, but look at A. A is a 5. That's going to make this so messy. Completing the square here, you could have 4/5 as the b value. You could have 2/5, or negative 2, or positive 2/5, I guess, when you add it over. It would become really cumbersome, right? There'd be a lot of room for error with completing the square here. So I would not choose completing the square. I would choose the quadratic formula. If A is a number like 2 or 1, then completing the square is very useful. Okay, it's very useful. But I would go with quadratic formula. So I start by listing it. If you don't want to list it, I really don't care, but as long as you do it correctly. If you don't list it and you make a mistake, I'm probably going to give you a hard time about it. Okay, so if you don't list it, it's fine. It doesn't matter, but you have to understand how to apply it. So B is 4, A is 5, and C is negative 2. So just apply those in the formula. Where you see opposite or negative, literally just switch the sign. Okay, I think I can leave this to you to try it yourself. So go ahead and plug in, see if you get the same thing, please. So remember that what's under the radical is called the radicand. The radicand has a lot of effect on this problem. And we're going to talk in section 7.3 all about the radicand. B squared minus 4ac. That quantity, that expression, is the focus of the entire next section, actually. And you could kind of already predict the implication of it. If I have a negative, what's going to be, right? It's under a radical, negative under radical, imaginary, positive under radical is a real number. So we're going to see how this applies itself to these topics in the next section. But for now, for a radicand here, I'm going to look at, what, 14? Is that what we end up getting? 14 for this? Or no, 56, which is 2 root 14. That's why. So we get 56 here. Let's reduce 56. 56 is divisible by 4. It's 4 times 14. And then I can see here that everything is divisible by 2. Remember, the radicand does not get reduced. What's inside of the radical cannot be affected by what's outside there. So if I look at this, I can think of this as, all right, let me factor out a 2 out of the numerator. If I factor a 2 out of the numerator and the denominator, in the numerator I'm left with simply negative 2 plus or minus root 14. And then the 2's cancel. There's my reduction. Okay, reduce these all by factors of 2. Recognizing that the 14 is not affected by the denominator. Because again, this 14 is its own separate entity, it's its own factor. If I reduce the 2, I'm already reducing this as a factor in general. The 14 stays itself. It's like if that 14 were like a y value, you could not reduce it. Right, so this is my solution for this problem. What does that mean? Plus or minus, what does that mean? What does that mean, plus or minus? When you see plus or minus? Look.
It could be
Yeah. Your answer is going to be, ready? Negative 2 plus root 14 over 5. That's one answer. And then negative 2 minus root 14 over 5. That's the other answer. And it's really interesting to recognize that you have two answers. They are binomial conjugates. Remember that term, binomial conjugates. We talked about it earlier already. If it's imaginary, we call them complex conjugates. These are binomial conjugates. They are both of your solutions. Now, what was the degree of this original polynomial? What was the degree? What does degree means? Well, let's ask it. 2. Highest exponent, right? 2. With second order or second degree here, you're going to get two solutions. These are your two solutions right here. They are not integer values. They are not imaginary values. They are irrational, and they are binomial conjugates. Okay, we're going to talk about classification of roots at a certain point in the next section, so I'm just emphasizing that right now. Okay, but you have two answers, and they are binomial conjugates. Let's revisit that problem we talked about earlier in the year, one-dimensional vertical motion. So here's the problem, right? The marker problem, where either it's dropped like this, or it's tossed straight up and it comes back down. I do coach baseball too, I swear. So you toss it straight up, it comes back down, but it lands in the same spot it started, or somewhere higher, but it's moving only vertically. It's not moving horizontally. One dimension, vertical dimension. So recall the formula. V0t minus 4.9t squared. The projectile is fired with a given speed of 20 meters per second, vertically up. Okay, vertically up. If I called that a velocity, I would know it's up. But because speed doesn't indicate direction, I'm saying up so you know. So here's launching, right? It gets launched with 20 meters per second as its velocity. If the height of the cliff is 50 meters, then when will the projectile, two things, reach the ground, and pass the top of the cliff on the way back down. We did this earlier in the year with a hot air balloon, and we saw when does it pass it on the way up versus the way down. Now we're looking at a problem that's similar, but what do you think is going to make this a little bit tougher? Anyone remember earlier in the year when we did this, what happened? I made the numbers work out really well for you earlier in the year. So what were you able to do earlier in the year when you had to solve this?
Get a numerical value.
Yeah, and you were able to, how were you able to do that though, to get the numerical value? How did you solve the quadratic earlier in the year?
Plugging the first.
No, not plugging the numbers, be careful. Someone else should do first. Not perfect squares, another right word you look for there. If you're not going to use the quadratic formula, you wouldn't use it because you can do what in this equation instead? Factor. Earlier in the year, it was factorable. I don't know if that's even a word yet. It could be factored. Okay? But in this case, we're going to see that when you plug in that 20 for V0, right, our equation becomes this. And if I want to know when it's going to reach the ground, what's the height of the ground? If the object starts on the ground, gets launched up, comes back down to the ground, what is the height of the ground? 0. So part A is saying, you know what? Let's find the zeros of this function. Let's find the zeros of this function. Well, in the first example, you might be tempted to use the quadratic formula because it looks like you can't really factor this. But you could factor something out. What could you factor out of the whole thing? T. So this first one we're going to see that we don't need the quadratic formula to solve. But we really can't factor into two binomials, although we are factoring. Okay, we factor out a t, we're left with 20 minus 4.9t on the inside. All right, take a t out of both of these terms, factor a t out of here and out of here, and that's what we get to. And this is easily solvable then. You get two answers. You set both roots equal to 0. Because of the zero product property, either root or either factor could be 0, giving us two roots. One of the roots is t equals 0 on the left-hand side there. The other root? What do we get? I don't have my calculator in front of me. 20 over 4.9. What's the exact value, or the approximate value, rather? What do you got? It's about 4, but do we have a tenth or anything or no? You have calculators, you can use them to check the exact value or approximation. 4.08? Okay. So around 4.1, because it's not exactly 4, so I don't want to put 4, which implies that it is 4. It's approximately 4, yes, I could have put approximation symbol. So 4.08. Why is time equals 0 a reasonable answer again? Where is this projectile at time equals 0? Where is it? It's on the ground. It hasn't launched yet. That's time equals 0. After it launches, it's time equals 1, time equals 2, turns around, time equals 3, time equals 4.08 when it hits the ground again. So how could I don't need this number, but how could I find the time to max height? Half of this, 2.04. Is that clear? And if I wanted to find the max height, I could take 2.04 and do what with it? You had the last one, you have this one too. If I want to find the actual height for the maximum value, I want to know what is this height, not how long does it take to get here, but physically what is the height? Not necessarily, because there's gravity involved. That was if there's constant speed. Plug it into the equation, right? The equation represents y of t. Y is the height. So you do y of 2.04 to give you the maximum height itself. But this problem didn't ask for max height. It said, when will it reach a height of 50 meters, which is the top of the cliff, and on the way down, not on the way up? Because remember, here it is, ready? It gets launched. It reaches cliff height of 50 meters. It passes it, turns around, comes back down, passes it again. So how many times is it going to reach 50 meters? Twice. How many answers do you get for these kinds of equations? You get 2 answers. So let's go to part B now. And part B is saying, when is it going to pass the top of the cliff? So we know the height will be 50 meters. So we can set the height, which is y of t, we could set the height equal to 50 meters. And now we'll recognize that we clearly have to use the quadratic formula. I'm going to write it in standard form. I'm going to move everything over to the left-hand side so that I have a positive a value. I know it sounds trivial, but it actually does help in your solution. It makes life easier to make a positive, so your denominator is positive. It's just less room for error. So I'm going to make this 4.9 t squared by moving it over. The 20t I'm going to subtract. And then the 50 is a positive over there on the left-hand side, so I'll leave it as a positive. So there's my governing formula right here, my governing equation of motion when we're solving for the height at 50 meters. Go ahead and use your quadratic formula, please. So again, an application of this example of quadratic formula here we're going to see. I want to change the wording of the problem. I'm realizing I did my wording off a little bit. So if you're looking at the wording of the problem, let's say it's fired from the ground to the cliff. Because I'm realizing that the approach of this problem that I wanted to take for you guys involved it being launched from the ground. So it says in the problem a projectile is fired from a cliff. Let's say from the ground. Okay, from the ground. You get 2 answers. Give me decimals, please. I know they're going to be square roots and stuff, but give me decimals. You want approximate times. Approximate times. What does your radicand become, by the way? When you do 20 squared minus 4 times a times c, what do you get under the radical?
580.
Exactly 580? Yes? No? Underneath the radical, did you get 580?
Yeah.
Yes? I'm thinking about it. We got b squared is going to give you 400 minus 4ac. Are you sure it's 580?
-5. Yeah, I got -5.
Okay.
Oh, yeah, that's right.
Yeah. That's possible. Let me think. Maybe because I changed the problem up, it wouldn't actually reach the height of the cliff. Let me think. 20 meters per second. You want it to reach a height after the first second, it's going to lose 9.8. All right, so I think changing up this problem might have screwed it up a little bit. Are you getting a negative under the radical? Do others get a negative under the radical? All right, so let's discuss the significance of this because I'm realizing that changing up the problem might have screwed it up a little bit. So the projectile is launched from the ground and it wants to reach a height of 50 meters. If it doesn't ever reach a height of 50 meters, it's never going to make contact. So the answers that you're going to get for possible solutions, you'll get imaginary solutions because of this negative underneath the radical here. So if both of your times turned out to be imaginary, it's not possible for this to actually reach that height of 50 meters. And that's how you can conclude for an answer. Now, obviously, had you gotten two answers, which answer would you have chosen? Had you got an answer of, say, 3 and well, what would it be? Let's say 1.5 and 3.5. Say those were your answers. Which answer would you have picked? Why? Yeah, because it's on the way down. So if the answers were 1.5 and 3.5, hypothetically, right? That means that it passes the height of 50 meters after 1.5 seconds, and then again after 3.5 seconds. So you would have chosen 3.5 if it was on the way down. Okay, I changed up the problem, realizing I think you screwed up. That's why we're getting a negative in here. Okay, others do verify though. I heard Jeff and Chandler, you said it was negative 580. Is that correct? What you got under there? Okay. All right, good example, but a good idea of why like a simple change to the problem completely affects it, right? And understand the significance of an answer that is really no real solution. This solution is imaginary. You can't ever get an imaginary answer when you're looking at applications of time. Okay, it just indicates that there's no actual solution possible. It will never reach 50 meters. Last example here. Let's take a look at this last one. Let's go through the process of solving this and coming up with a solution that is in simplest radical form, but it's also going to be a complex conjugate. Okay, so let's practice this one together, going through this to see what we get when we have a complex conjugate. So I'd start by moving 3 over right away. Then I go right to my quadratic formula. M equals negative 5 is positive 5, plus or minus the square root of, remember that negative 5 is squared, so b squared is always going to be a positive quantity. So if you don't want to put negative here, I really don't care, but just recognize that this negative is being squared. This should be positive. Do not get a negative number there, please. Okay, b squared minus 4ac all over 2a. So we're going to have 25 minus, we have 4 times 3. 16 by 3 is going to give us 48. 25 minus 48, negative 23. All over 2a. How do I write this as an answer then? If I have a negative, Morgan?
5 plus 23.
Yeah, I root 23. Right now, if I was writing it in standard complex form, we've been talking about a plus bi form. Okay, that's what it would look like in standard form or complex form. All right, tonight practice this. You have homework to practice. Take a look at it, please. There are some word problems in the homework. There are regular problems and word problems. If the regular problems get really easy and you're running out of time, I'd rather you focus on word problems. Okay? So maybe you can start with the word problems if you'd like to. We'll see a few more of these in the next few days.